Alright, welcome back folks for part 3. So, let's take a look at a few examples. So, the common reference component in a lot of books, even in ours, but we're going to talk about two long peptides, short polypeptides. We're going to talk about vasopressin, our top one here, and we're going to talk about oxytocin, our bottom one here. And so we've written out just the amino acids. I've got a cysteine, a tyrosine, phenylalanine, glycine, and so on and so on and so on and so on. The exact names, like I said, you don't have to remember what each amino acid is. What I want you to see between the two of them, though, is that most of them are the same. Cysteine and cysteine, tyrosine. Number 3 is different. But 4 is the same, 5 is the same, 6 is the same, 7's the same, 8's different, 9's the same. Most of these are identical. It's just got two tiny little ordering difference. And so we've swapped 2 of the 9 amino acids out for different amino acids. What does that look like? And then, what does it mean that 2 of them are swapped, and how does that change things? So let's take a look down below. These are the structures, I'm going to go through them bit by bit, of oxytocin over on the left, and vasopressin over on the right. So let's pick green. Here we go. Number 1, cysteine. Well, cysteine was one of our special amino acids. It is a CH2SH. Now you'll notice it draws them connected. There was a reactivity for thiols. Remember, if you had RSH and you had 2 of them, they could react to make a disulfide bond. Now, we didn't do much back in reactivity with this, but why it was important is that it comes up here for cysteine. It's a very common thing for cysteines to link together. And so these 2 cysteines actually end up helping us cause a circular component. Because let's look, here's one amino acid, and it's got cysteine. So here's number 1. As we get to number 2, tyrosine, it is this ring with the OH, and we see the same bits over on vasopressin. So oxytocin and vasopressin start the same. 1 and 2 are identical. As we keep following our amino acids, so here's the nitrogen, the carbon with the R group for 1, double oxygen. New nitrogen. That is their second carbon with an R group. And we see that, it's tyrosine, the ring with the OH on the end. And then the carbon double bond oxygen. Third nitrogen. Down to the 3rd carbon that has an R group. We find that over on the other structure. 3rd carbon that has an R group. Except what that R group is now different. In fact, let's clear that and go to the color we were using. Yellow. This 3rd position has changed. Instead of being a reasonably bulky nonpolar group, it's become a very flat nonpolar group. Now it's still nonpolar, but the geometry is a bit different. The lengths, the angles, and the fact that it's very flat. As we keep going around the molecule, things after that are the same for a while. 4 and 5 and 6 and 7 were identical. And what we'll find is, sure enough, as we go from the 3rd carbon with an R group, we run into the double oxygen to the next nitrogen of the next amino acid. So here's the 4th. Same over here on vasopressin. We go to the 5th. So find next nitrogen, next R group. It's this dangling amide, and sure enough, we find there's this dangling amide on the other one. Sixth was cysteine on both of them. And sure enough, we find sixth is cysteine on both. And we see the disulfide connection. Our two cysteines have linked together. So instead of one long line, we basically curled it over to link the cysteines together. 7 is the same on both. We see it drawn in this one. 7 is proline. It was the odd one that links back around. The drawing here for oxytocin has it as two separate R groups. But the idea is it links around. And then 8. Arginine versus leucine. 8 was different. And sure enough, what we find is as we get to number 8, our 8th carbon polynitrin, arginine is this nitrogen-heavy large cation, and leucine is this 4-carbon small non-polar bit. The last one, glycine, is the same on both. Glycine has a hydrogen for its R group, so it doesn't seem to have anything. And then you'll notice, we didn't draw it before, highlight anything about it. But you notice we ended with NH2. Now I said before, we always start with the N terminus on the left. In fact, we saw that in our structures here early on. Run out of colors. We started with the nitrogen. That's not the same NH. This is way back here on number 1. This is the nitrogen of cysteine. But glycine had its own nitrogen. That was the one that started here and then went. So here was the glycine nitrogen, went to its R group, and it should have ended in a carboxylic acid. Often, biology will slap an amine on the end to seal the carboxylic acid. Not always, there's a few other things. And in fact, they often slap other groups, acetyl groups, like acetic acid, onto the amine to close it up. Like they're rarely left as free amines and free carboxylic acids. It's a little outside where we are now, but since it's on the image, I figured I'd highlight it. That purple nitrogen, biology actually clipped it on into the end of the carboxylic acid just to seal up and get rid of the carboxylic acid. Remember, carboxylic acids normally are, well, they're normally acid. They give away their proton, and they're anionic in the body. By putting the amine on there, makes it neutral. And so it's less reactive, and it dissolves better in certain situations. So what we've seen here, two very similar structures. There's a ring and then a tail. There's a ring and then there's a tail. These are larger molecules that are constructed by linking together a series of small molecules. This is how all of our peptides, polypeptides, and proteins go together. They're just linked in series. Sometimes there's disulfide bridges, sometimes they're not. We'll talk more about their structures and everything as we get further into the protein section. Right now we're just on the amino acid section. So, very slight difference, just those two yellow groups. But how does that play out? Well, these molecules are hormones. They are signals to your body. They don't necessarily do much on their own, but because they have a slightly different shape, they just fit into things different. Think about your keys. They look largely the same, but only one tends to fit your door. Those little teeth difference make a difference in what it connects to. By swapping out a very polar group for a leucine, a very non-polar group, between vasopressin and oxytocin, so that arginine to leucine change, that is a significant change. Whatever is interacting with these, so there's going to be some other molecule that this is fitting into. So that other molecule is going to have some kind of flat nonpolar and might have its own ring systems here. to interact with. It's going to have some kind of OH to hydrogen bond with there. It's going to have some kind of hydrogen bonding going on over here. Whatever that molecule is, definitely wants the right type of interactions for this to fit. And it has to have a big space, and it has to have some kind of negative to interact with the positive. Well, if you tried to fit oxytocin into that space, it would have largely the same for a bit, except it would have a big hole here where it would have these negatives, and it wouldn't have anything to interact with. There's no polar attraction like there is over here in the vasopressin. And so oxytocin doesn't fit that same shape. It has its own shape that it fits in, but it's just slightly different. Notice the biggest different regions are just right here. This one has that space with some anion, and oxytocin's doesn't. What that means is that it clips into different parts of your body to give the signal. Oxytocin is used in pair bonding. Sometimes it's called the love hormone. You hear false stories on the internet about how voles who mate for life have very high levels of it, things like that. It's not anywhere near that simple, but it does come up in bonding. New mothers with infants will have a higher level of oxytocin because it encourages bonding in that fashion. Vasopressin, on the other hand, is about water retention. It signals the body to retain water. It's not exactly important for bonding. It's a very different interaction because, well, again, it's the interaction. It just doesn't fit the parts of our brain that have receptors that tell us to bond with something more, like oxytocin does. Instead, it interacts with kidneys and other things to help us retain our water. And so when we're dealing with proteins, small changes can have big effects because it's not always about what that molecule itself does. That molecule might just be telling something else to turn on. And, well, if you use a key to open your door versus a key to start a monster truck, very different things happen, even though they're pretty similar in structure. And so I wanted to give an example here and be able to show you and walk us through kind of looking at a molecule built out of amino acids.